Ved Prakash, can you unmute your microphone? Ved Prakash, can you unmute?
Yes, sir.
Lot of sound is coming. Yeah. Please unmute your microphone here.
Okay, sir.
Oh. Okay, my dear students. Yeah. So what we discussed till now, it is basically the nanomaterials, the nanotechnology, what are the approaches, what is there in nanotechnology, so top-down approach and bottom-up approach. So we also have compared the top-down approach with the bottom-up approach. What are the advantages and disadvantages of both approaches? And later part, we just switch on to the different synthesis processes. So we discussed mechanical type, just a physical type in the form of a ball milling process, and we have bottom-up process in the form of the chemical sorry, vapor gaseous phases, GPC and CVC, as well as the pyrolysis method, soil gel method. All these are all what we call, these are all the process, the synthesis process of nanomaterials. So the second part of this module 5 is characterization techniques. So the module itself is a nanomaterials and characterization techniques. So till now what we discussed, it is about nanomaterials and their synthesis. The second part of this module is characterization. So characterization means, so in order to what the materials you have manufactured or synthesized, so whether are having the correct size, correct shape, whether they have been distributed uniformly across their structure. So these things we need to identify, we need to obtain the details of the information. So how you can get this information? Because these are all, what we are talking is, it is at the nano level. So we discussed the macro, micro, and nano. We are just, it is in the range of 10 to the power of -9 meters. So definitely it's not not visible to your naked eye. So then how we can go ahead? One, how we can ensure the size of the particle, the shape of the particles, and the microstructure, the distribution. So these things we need to ensure whether they have been occurred properly within the structure. So for that, there are certain methods, what we generally term it as a characterization techniques. So these techniques will help us to know what is the shape, the size, structure, distribution, everything within the material. The purpose of this characterization is to control. So because there are certain properties that the material can exhibit. That's what I was talking in the first class of this module. See, why do we need the nanotechnology? Why do we need to go up to the bottom level? Because there is a plenty of rooms or roads across the bottom. What's the statement what we have? So if that is the case, why do we need to go up to the atomic level or up to the nanoscale? So the main reason is for that is, at the nanoscale, the properties have its unique properties. Means the properties can exhibit its unique properties only at the nanoscale. Those properties can be used for various applications. So what properties and how to control those properties? Because controlling is very, very important here. So to get a desired property, you need to control certain parameters while you are synthesizing the material. So how to control that and what to control is the most important thing. So how to control and what to control. So how to control, we have so many techniques, and what to control. So whether the parameters are controlled or not, that needs to be identified, that needs to be ensured before we just go for using those nanomaterials for the particular application. In this regard, the characterization techniques will come into the picture. These characterization techniques will help us to what are the parameters needs to be controlled, and we can ensure whether the parameters are controlled or not. So once you control these parameters, then we can ensure that the materials are exhibiting the unique properties across their nanoscale. So to ensure these controlling properties, whether it is before the synthesis or after the synthesis, we need the techniques, what we call it as characterization techniques. Okay, so now we discussed how we can synthesize the nanomaterials. Now move on to the characterization techniques. So what are the different techniques available for us? Okay, so we're going to discuss in this second part of the module. So let's start now. There are so many methods are available for us. There are so many characterization techniques available for us. But in our syllabus, we have only 7 techniques that have specified. So all these 7 techniques, we need to discuss the principle, the imaging modes, applications, advantages, as well as the limitations of 7 different techniques, characterization techniques, using optical microscopy, scanning electron microscopy, in short we call it as SEM, transmission electron microscopy, TEM, of course optical microscopy is called OM. So I think I just forget to write that. Optical microscopy OM, scanning electron microscopy SEM or STEM, transmission electron microscopy, we call it as TEM, transmission electron microscopy TEM, X-ray diffraction XRD, scanning probe microscopy SPM, atomic force microscopy AFM, and electron probe microanalyzer EPMA. So these are the 7 different characterization techniques. We need to discuss the principles, imaging modes, applications, advantages, as well as the limitations. So these are the 7 techniques we have in our syllabus. Okay, so we'll start discussing one by one. So I think today, if possible, we're going to complete 1 and 2, the optical microscopy and scanning electron microscopy. I think that is the only maximum I will just try. Next thing is another remaining 4 we'll be going to discuss in the next classes. Okay. Yeah, let us start with the first one, optical microscopy. This optical microscope, first I am going to start with the first one, optical microscopy. The optical microscope, often referred to as the light microscope. Light microscope, I think this type of microscope you might have seen in your physics lab or your metrology lab, so where the image will be formed with the help of a light source. And it uses the visible light and system of lenses to magnify images of the same small samples. I think you might have done the experiment on preparation of specimens for metallurgical or microscopic study in your metal testing laboratory. So there you might have done the experiment for how the specimens are prepared and how you can observe the microstructure through the microscope. Okay, optical microscope. So the same thing over here. So here in this case, the visible light and the system of lenses, or both are used to magnify the images of the small samples. The samples are very small, and when you keep just below that objective lens, okay, so you can easily focus it and you can see the microstructure or images, we can say the magnified images, which is obtained by the help of a visible light and a system of lenses. And of course, the optical microscopes are the oldest design of microscope and were probably designed in the 17th century. The basic optical microscopes can be very simple, but there are many complex designs which aim to improve the resolution, and the sample contrast. Yeah. Historically, optical microscopes were easy to develop and are popular because they use visible light so that samples may be directly observed by the eye. Yeah. The image from an optical microscope can be captured by a normal light-sensitive cameras to generate a micrograph. So when you attach a cameras, light-sensitive cameras, and you can capture the images and you can generate the micrographs. Originally, images were captured by photographic film. Modern developments in CMOS and charge-coupled devices, CCDs, cameras, allow the capture of digital images. So you are using a digital image, the digital cameras, and you can get the picture or the image can be captured. Purely digital microscopes are now available, which use CCD cameras to examine a sample, showing the resulting image directly on a computer screen without the need of eyepiece. Of course, nowadays we are having CCD cameras, charge-coupled devices, cameras to examine a sample, showing the resulting image directly on a computer screen without the need of eyepiece. No need of looking at the sample, just keep the sample below the objective lens and take the picture. And CCD cameras are fixed over there, and this CCD cameras directly will going to capture the image and it will going to display it on your computer screen. So this is the latest pure digital microscopes what we are using now. So here, the optical microscopy is a type of microscope which uses visible light and a system of lenses to magnify images of a small sample. The definition. The image from an optical microscope can be captured by a normal light-sensitive cameras to generate a microscope. This is what we think. Right. So what you have: human eye, eyepiece, projector lens, intermediate image, objective lens, specimen, condenser lens, light source. This is how the process will go, and this is the diagram of an objective microscopy, optical microscopy. See, this is the diagram what you are supposed to, the ray diagram what we call it as, how the light rays will go and you will going to see this one. Now you can see the images. So here we are having an eyepiece. So here we have a projector lens, then we have an objective lens and the specimen, condenser lens and the light. Okay, so this is, I think this you might have seen the optical microscope in your lab. You know how to use this optical microscopes. Okay, so this is the basic schematic diagram of an optical microscope. Okay, so the function is to create a magnified image of a specimen consists of three basic functions of obtaining a clear sharp image, changing a magnification and bringing to focus. So how to get this? That is, you have to keep a specimen on the table over here. So table is below the table there is a condenser lens and you will have a light source. Okay, so at the top of the table, so there is a platform where you are going to keep the specimen, and the specimen will be exposed from the bottom. The light source will be there, and then the condenser lens. Through the condenser lens, the light will going to be transmitted. Since you are using a light, you can see the images. That's why the light source will be there at the bottom over here. So now this is the at the top you have an eyepiece, okay, and then there is a projector lens and the objective lens. So a person who has to see the structure of a specimen which is been kept on the table. So this is an eye. He will going to see through this eyepiece. Okay, so his rays will go through here. See, this is, I will show the ray diagram later. Next slide we have got that. So I will show that. Okay, so this is the process of what? How you can capture the image. How you can see the image through this eyepiece. Okay, so projector lens is there and the objective. Projector lens will going to project the images. Okay. The function to create a magnified image of a specimen consists of three basic functions. One is of obtaining a clear, sharp image, changing magnification, and bringing to focus. These are the three important functions of to create a magnified image of a specimen. The principle is like this. Look at here. So this is the ray diagram what you can might have understood from your physics. Okay. So to create a magnified image by combining the objective lens and making an inverted real image and magnifies the image further more with the eyepiece to allow the user to observe it by a naked eye. So this is what the optics. Totally, it is an optics. Okay, so where you can eyepiece is there, you can see eye, focal length, see here, the inverted real image. Making an inverted real image and magnifies the image further. The objective lens. The purpose of objective lens is making an inverted real image and magnifying the image further with the help of an eyepiece to allow the user to observe it by naked eye. This is the principle of optical microscope. I think this you might have been studied in your physics or in your chemistry or whatever it might be, how it will go into work. This is the optical tube length. How much length? This is the focal length, and here is the focal length. Okay, so this is how the principle going to happen. Applications, when it comes to the applications of optical microscopy, so it is used in microelectronics, nanophysics, biotechnology, medical diagnosis. Okay. And advantages: medium cost, simple devices, fast and adaptable to all kinds of sample systems, easy to be integrated with the digital camera systems for data storage and analysis. So these are the some of, because these microscopes are not expensive and they are very simple devices, and the process of using is very fast. Can easily capture the images with a very small interval of time, and it is adaptable to all kinds of sample systems. Know that you need to have this only this type of samples, any kind of sample systems you can use. And most important thing is they are very easy to integrate it with digital camera systems for data storage and analysis. The main disadvantage of this type of microscope is limited to the magnification factor. So you cannot go to the high level of magnification. And the another one important thing is the resolution. Resolution is also very small. So these are the two main disadvantages makes optical microscopy uh, not to use in the research purposes nowadays, because you don't have a higher level of magnification. So because when we are using it in the nano levels, nano scales, it's since the magnification and the resolutions are very less in the case of an optical microscopy, so it will have a very limited usage in the research purpose. So therefore, the major disadvantage of optical microscopy has been overcome by the another two microscopes, what we call it as scanning electron microscope and transmission electron microscope. This is what we are going to discuss in the later part of the class, right? So where the high level of magnification and the high level of magnification, sorry, low level and the low level of magnification and low level of resolution will makes the optical microscopy to be used very limited in the case of research. So therefore, so we need to discuss the next type of microscope, what we call it as scanning electron microscope. So before going to that, some have pictures here. Of course, these things you might have seen in the lab. The modern microscope with the mercury bulb for fluorescence microscopy. The microscope has a digital camera and it is attached to the. So this is the basic microscope with the what we call it as integrated with the digital camera and connected to the computer. See here, the camera has been fixed over here. Okay, so no need of eyepiece here. The sample is kept over here. So once you keep here, camera will go to take the picture and will go to send to the computer. So you can see the images over the computer directly. It is a digital camera integrated microscopes, the modern microscopes what we are having now. And uses, of course, that's what I will discuss applications here. So microelectronics, nanophysics, biotechnology, pharmaceutical research, mineralogy, and microbiology used for medical diagnosis when dealing with a tissue in smear tests or free cells or tissue fragments. In industrial use, binocular microscopes are common. In certain applications, long working distances or long focus microscopes are beneficial. An item may need to be examined behind a window, or industrial subjects may be hazardous in the objective. Such optic resembles telescopes with a close focus capability. This is what the uses of optical microscope. So this is the first thing what I wanted to discuss with respect to the optical microscope, the first thing. Right? The second important thing here is the scanning electron microscope. So what is the scanning electron microscope and what is the advantage of scanning electron microscope over optical microscopy? We will go into discussing details. Yeah. See, because the optical microscopy has got a limited magnification and limited resolution, so it is quite very less it is used in research purpose. So therefore, nowadays in research, we are using only the scanning electron microscopes, or we are using the transmission electron microscopes. Okay. So now let us discuss what is the scanning electron microscope, what is its principle, how it works, what are the different components of the scanning electron microscopes. All these things we will go into discuss. Okay. The scanning electron microscope produces images of a sample by scanning it with a focused beam of electrons. In the sense, the basic principle in SEM is the focused beam of electrons. focus beam of electrons will scan the sample and it produces the images. The electrons interact with atoms in the sample, producing various signals that contain information about the sample's surface topology and composition. So this is the principle over here. The electrons will going to interact with the atoms in the sample. So when you just focus the beam of electron over a sample, and these electrons will go into interact with the atoms within the sample, and once they interact, they will start producing the various signals, and signals which contains the information about the sample surface topology, topography, and the composition. Okay. Let us start with the basic principle. An electron beam is focused onto the sample surface kept in a vacuum by electromagnetic lenses. A beam is scanned over a surface of the sample. The scattered electron from the sample is then fed to the detector and then to the cathode ray tube through an amplifier, where the images are formed, which gives the information on the surface of the sample. What it says here is a electron beam. Electron beam, you are going to keep a sample over a surface or a table, and you are going to focus a electron beam over the sample surface. And this sample surface should be kept in a vacuum by electromagnetic lenses. Means you are going to focus the electron beam by electromagnetic lens, which is kept in the vacuum. This beam will scan over the surface of the sample, and the scattered electron from the sample is then fed to the detector and then to the cathode ray tube through the amplifier. So the electrons which are scattered from the sample, so once the beam is focused over the sample which is kept on the table in a vacuum by electromagnetic lens, these electrons will get scattered from the sample, and then it is been fed to the detector and then into the cathode ray tube through an amplifier. So in this amplifier, the images will be formed, and these images will give the information of the surface of the sample. This is the basic principle behind parts, the heated filament as a source of electron beam. So instrumentation means different parts of this scanning electron microscope. Heated filament as a source of electron beam, condenser lenses, evacuated chamber, electron detector, amplifier, CRT, cathode ray tube with image forming electrons. So these are the different parts of the scanning electron microscope. One is a heated filament, condenser lens, evacuated chamber, electron detector, amplifier, and CRT with image forming electrons. I think you can see all these things over here. Okay, so this is the sketch of a scanning electron microscope. So this is an electron gun. Okay, so you will have a condenser lens. This is an evacuated chamber. Evacuated chamber. This is an electron detector. This is the sample where you are going to keep. Okay, and we have an amplifier. So amplifier is here, and we have a CRT. Okay, so this is the diagram of just a simple line diagram of a scanning electron microscope. This I think you can see in much more detailed way over here. So the electron gun, which forms the electron beam. This is an anode. The magnetic lens kept over here. The scanning coils, Okay. Then we have electron detector and the stage specimen is kept over here. Okay. So this is the just a ray diagram how the electron beam passes through the different stages of the scanning electron microscope. Okay, so look at here how it has been passing over there. The backscattered electron detector. This is okay. The principal images produced in the same are three types. One is the secondary electron images, backscattered electron images, and elemental X-ray maps. These are the three important principal images are produced. See what happens, how it works. One is the three types of the images, or one is secondary electron image, backscattered electron image, and elemental X-ray maps. As the electron beam traces over a sample, it interacts with the surface of the sample, dislodging secondary electrons on the surface of the specimen in unique patterns. In the sense, as the electron beam is focused, is over the sample, so it interacts with the surface of the sample and it will go to dislodge the secondary electrons in the surface of the specimen with a different pattern. The secondary electron detector attracts those scattered electrons, and depending on the number of electrons that reach the detector, registers different levels of brightness on the monitor. So once the electron beam dislodges the secondary electrons from the surface, there is a detector, what we call it as a secondary electron detector. This detector will attract those electrons which are scattered, and depending on the number of electrons that reach the detector, registers the different levels of brightness on the monitor. Okay, so this is what the very important thing is supposed to be understood here. So as the electron beam interacts with the surface, it dislodges the secondary electrons which are there in the sample or in the surface of the specimen with a different pattern. And the secondary electron detector, it attracts those scattered electrons, and depending upon how many number of electrons that reaches the detector, it registers the different levels of brightness on the monitor. Additional sensors detects the backscattered electrons that reflect off the specimen surface, and X-rays emitted from the beneath the specimen surface, dot by dot, row by row, an image of, in the sense, original object is scanned into the monitor for viewing. So in the sense, there are electrons that will additional sensors detect backscattered electrons. So there is electrons which scatters from the surface, and they scatters back that reflect of the specimen surface. So this is the one thing. So electrons that reflects out back to the from the surface, and X-rays which are emitted from beneath the surface, specimen surface, and they will going to be detected by different detectors, and dot by dot, row by row, an image of the original object is scanned onto the monitor by viewing. SEM uses scanning coils which create magnetic fields using fluctuating voltage to manipulate the electron beam. This means there is a scanning coils, and they will start creating magnetic fields using fluctuating voltages, and it manipulates the electron beam. The scanning coils are able to move the beam precisely back and forth over a defined section of an object. If the researcher wants to increase the magnification of an image, he or she simply sets the electron beam to scan a smaller area of the sample. In the sense, The scanning coils are able to move the beam precisely back and forth over the defined section of the object. In the sense, these scanning coils will help us to focus the beam only to the particular area. Okay, so particular area or defined section of the object. So this will help us to increase the magnification. So means if you want to increase the magnification, in the sense we have to focusing it only with a particular area of the sample where I want to know what is the structure or microstructure of the component. So you can use the scanning coils, which will go into precisely move the electron beam to the back and forth over the defined section of an object. So this is how you can increase the magnification of the scanning electron microscopy. Right? So there are some applications they are specified here: characterization of solid materials, topographical, morphological, and compositional information. STEM can detect and analyze surface features, provide information in microstructure, examine surface contaminations, variation in chemical composition. And it also provides qualitative chemical analysis, identify crystalline structures, semiconductor inspection, examine microchips of computers, essential research tools such as life science. Like that, you can have so many applications. I'll discuss this in detail in much more thing in the next one. Okay, and coming to the advantages. They are easy to operate with a proper training and advanced computer technology, and associated software make operation more user-friendly. Works faster. EDAX analysis is completed within 5 minutes. Generation of data in digital form. Minimum preparation actions. Structural analysis. Powder morphology. Particle size and analysis. Delamination investigation. Examination of surface morphology. So there are quite a number of advantages of this STEM, and disadvantages: it is little expensive. Large, and must be housed in an area free from any possible electric, magnetic, and vibration interference. Means it needs some controlled atmosphere, and special training is required to operate that, and maintenance is high. Involves keeping a steady voltage currents to electromagnetic coils or circulation of cool water, risk of radiation exposure associated with electrons that scatter from beneath the surface. So these are some of the major disadvantages of STEM. So I will take some more little understanding of this STEM. So I think I have time. I will just check it out. Yeah, I have another 15 minutes time. I will just complete this. Yeah, we are talking about the construction. We have some more clarity here. Electron gun, condenser lens, objective aperture, scan coils, chamber detectors, computer hardware and software. The scanning electron microscope is this. This is the electron gun, vacuum chamber, condenser lens. Again, we have a condenser lens and objective lens over here. The sample chamber will go secondary detector, backscatter detectors. Okay, so this is the diagram what we are showing. How the STEM works. The STEM uses electrons instead of light to form an image. A beam of electrons is produced at the top of the microscope by heating of an metallic filament. So you have a metallic filament. When you heat it, it will go into release the electrons. The electron beam follows a vertical path through column of the microscope. It makes its way through the electromagnetic lenses, which focuses and directs the beam down towards the sample. So this is the lens system over here. So once the electrons are produced in the electron gun and maintaining the vacuum chamber, so it passes through the condenser lens. So it will go into focus this electron beam towards the sample surface. Okay. Once it hits the sample, other electrons are ejected from the sample, backscattered or secondary. So means there is a once these electrons will hits or it will going to impinge over the sample, the other electrons they will get ejected from the sample. So then we have the detectors, X-ray detector, okay, we have secondary detector, we have backscatter detectors. Like that, there are three different types of detectors are there. So those detectors will go into detect the electrons. Detectors collects the secondary or backscattered electrons and convert them into a signal that is sent to the viewing screen similar to the one which ordinary television are producing an image. So the backscattered or secondary detectors will detect that and it will go into convert them into a signal and it will go into set into the viewing screen. This is the basic working principle of a SIM. Okay. And how this then works, we discussed. Now comes the characteristic information of SIM. So topography, the surface features of the object or how it looks, its texture, direct relation between these features and material properties, that is a characteristic information what you can obtain from the topography. Then morphology, shape and size of the particles making the of the object, direct relationship between these structures and material properties. Okay, and then composition, the elements and the compound that the object is composed of and the relative amounts of them, and direct relationship between composition and material properties. Crystallographic information, how the atoms are arranged in the object, direct relation between these arrangements and the material properties. In the sense, what you can obtain, the characterization, what I am talking about. So you can get a topography. Topography means the surface features, the texture, and the relation between these features and the metal property. Second comes morphology, the shape and size of the particles and the relationship between the structures and the material. Composition, so elements and compounds that the object is composed of. So composition you can obtain, and crystallographic information. So how the atoms are arranged. Topography, morphology, composition, and crystallographic information. These are all the important characteristics what you can obtain from the thing. And these are all the some of the things you can see the pictures. How does it looks like in SEM? A from cantilever tip, ant head. Look at here, ant head. How it is looking now. So ant is just a 5 mm length. So you can see the ant head, how big it is. Blood cells, what we are getting. Diamond thin films, microstructure of plain carbon steel, calcium phosphate crystal. So these are all the images what you have got it from the SEM. Okay, and this is the objective aperture. I don't want to discuss. And quickly, we have a difference between optical microscope and electron microscope. Optical microscope uses source of light. Here, the source is replaced by a beam of fast-moving electrons. The lenses, the specimen usually has to be specially prepared and held inside a vacuum chamber from which the air has been pumped out. Since you are maintaining the vacuum, so here not required for the optical microscope any kind of specimen, any shape you can do, and no need of vacuum over here. In the case of optical microscope, the lenses that makes the specimen seem bigger. So lenses are replaced by a series of coil-shaped electron magnets through which the electron beam travels. The magnified image of the specimen that you see here, the image is formed on the photograph called an electron micrograph, or as an images on the screen. So this is how it looks like inside the column. So this is a scanning electron microscope, electron gun alignment control, pneumatic airlock valve, condenser lens, objective aperture, scanning coils, objective lens, motorized stage, and sample chair. This is a typical images produced by SM. This is the scanning electron microscope image of a spider. Looks like a spider. How small the spider is. but looking like this spider. Just see how we are getting. And this is cultured human cells, artificially colored scanning electron microscope showing Salmonella typhimurium red, what is in red color, invading cultured human cells. Such a simple, very minute things looking like a very big elements over here. And this is the scanning electron microscope of bacteria Escherichia coli, E. coli. Okay, so these are all some of the images what you can get it from the cell analysis. Okay. So this is regarding the scanning electron microscope. Right? So anybody has got any clarification, any doubts? So you can talk to me before I just leave. The next class we are going to discuss with the remaining characterization technique. So you can interact with me for any clarification and any doubts before we just wind up. Any clarification, my dear students? So all our theoretical part, there are plenty of diagrams that will come into the picture. You have to practice these diagrams because each and every module, it is a theoretically based concepts. So number of sketches will come, so many process parameters, advantages, disadvantages, applications. So all these things you have to practice. Until unless you practice the diagrams, it's very difficult for you. So anybody wants to have any clarification, you can talk to me before we start. We just stop the class. You can unmute your microphones and you can speak to me. Okay then. So if you don't have any clarifications, I will just stop this class now. Okay, we'll just wind up the class now, and we're going to meet you in the next Friday's class, where we're going to start with the remaining characterization techniques. Okay, so I will going to post all these things in your Google Classroom, so you can start preparing for these things, and even module 4 material also I'm going to post it in the Google Classroom. So please refer those things in your Google Classroom and start. Okay. Thank you very much, my dear students. Thank you. I will just leaving the class now.